Okay, let's talk about something I call the Deformer basics. And the idea is understanding core concepts about how to deform geometry, basically. So what I did so far always to speed things up, because I was a bit lazy, is I simply used the grid, the good old grid, and I kind of emulated a mountain node. By doing this, I just changed the height of the position and controlled it by a noise. We've seen that. So there you go, and I have a simple thing that looks like a mountain node. But that's actually not correct, because this only works in this very particular case of the grid. As soon, of course, as I do this with a sphere, that falls apart. Why? Because I move, of course, the points. I don't even, here's the thing, I don't even change the position, I override it completely and I get this flat, pancake. So while this might be interesting and exactly what you were looking for, it's unlikely that this is what you need very often. Actually, what the mountain node is doing, if you think about it a little bit, is obviously it takes the position it already has and adds to it. That's the first thing. And then it kind of moves, how we would call it, outwards. Now, what means outwards in the 3D world? What is outwards? Actually, it's not a mystery. This is actually exactly what the normal is about. This tells you what outwards or forwards means in the context of a shape. So we can use the normal information, and here is an interesting thing. If you don't have the normal, then as we've just seen here, there is no normal attribute, but we can still visualize the normal because there is an implicit normal. This is kind of a nicety from side effects, otherwise we wouldn't see anything. And we have to basically, if we wanted to deform a geometry, move a point not upwards, not sideways, not in circles, we move it in the direction of its normal to push it forward, basically. So what that means is that not only do we have to add to the current position, so with a plus equal, which will do something. So let me quickly put a controller to control the strength to this by just multiplying the result, because this way we can see better what's actually happening. We currently add to the position, but by just adding something to the y, we just move it up and down. So what we want to do is we want to change the position and want to move it in the direction of the normal. And since the normal is a vector that is already normalized, which is the reason it is called a normal, we can, and we'll talk about this later, by the way, but we've already seen that, we can actually take this basically as a multiplier to whatever we want to do, and that defines the direction of what we're doing, basically. So if I just do this, you will actually see it instantly works. We've moved the points towards their normals. And again, what's actually interesting here is that we don't have the normal attribute, but this is implicit. So you don't necessarily have to rely on that. I usually do this out of habit, really, to make sure that I actually create a normal that is actually existing on the points, because this way I can be absolutely sure there is an attribute and it actually has reasonable data. But as you've just seen, you don't have to do that. Even if you don't have the attribute, it will be implicit for a normal. Actually, I made a mistake here, and one of you pointed that out with the help of the feedback function, so thanks very much. The problem here is actually when you look really closely and do this carefully, you can see that we're currently actually not moving in the direction of the normal. You can see it here in this area. The points are also moving to the sides, not just forward, so to say. And the reason is that this noise function here is currently actually creating a vector. And that is because, potentially, because it is multiplied with a vector, or it is because it's used for the position. So either way, this thing here, this part, is currently creating a vector, and this is why we move in the direction of the normal, but then also somewhat to the side. So to fix that, that should be straightforward to you. We just have to force this to become a float, not a vector. And then, as you can see, the result is different. And you can see now here that there's nothing moving back and forth anymore. And together with the normal node, the whole thing is now much cleaner and much more like a mountain node would actually behave. So thanks very much for pointing that out. Make sure that you turn the noise into a float. And then don't forget, if you do this, to recreate the normals afterwards. Because as you can see here, if you don't do that, then the result will still look like before in terms of shading, because the normals have actually not changed with the transformation of the position. This actually could be done implicitly. So actually I would expect, if you have no normal attribute at all, that this node will be rebuilding the normals, but that's not the case unless you actually tick this on, because here it is actually, there's a function for that called update normals if displaced. And now if I change this again, nothing happens. Why not? Okay, technically, if I turn this on, this should actually automatically update my normals. I can only assume that this is a bug. When I tested it before, it worked, but this was on a different version. Okay, so it is built in technically. Just drop a normal node, which has the advantage of me seeing what I'm doing. But I just wanted to tell you that there is a built-in function, which doesn't work. So as you can see, this is actually what a deformer is doing. It pushes points in the direction of the normal by a certain amount, and in this case by the amount of a noise. Another thing that is interesting, which is also built in the mountain, because if we move up the height, you can see it's actually, maybe if you look at the edge, it's easier to see. Well, actually we can't see it here. Maybe, where can we see it? Maybe if I make it bigger. Yeah. There it is. Yeah, okay, this here it's very obvious. So instead of pushing all the points outwards, it actually also pushes stuff inwards. And the idea behind that, so here it goes outwards, here it goes inwards. And the idea behind that is that let's call it the overall perception of the volume is not fundamentally changing. Of course it is changing, but since some stuff is pushed in, some stuff is pushed out, it doesn't result in a completely different volume. Whereas what we are doing here with our simple version of that, we are definitely changing the volume. It definitely gets bigger. And the reason, of course, is that we only add positive numbers. And this is just something I wanted to point out for you to realize. The mountain node has this function here, center noise, which means that whatever we add to the function, when we turn it off, we can see that will not just be added to the form, but the middle number will be the reference point, and everything below will be pushed in and everything above will be pushed outwards. How can we implement that in Vex? Actually quite simple, because you might already have guessed it. This thing we can trust, at least for a noise, that it will be between 0 and 1. Therefore, it's really that simple. We just subtract 0.5 from the result. And if you want to be absolutely sure, then we can put this into brackets. And as you can see now, if I change here my parameter, then the volume feels like it's not completely changing anymore. So very often this is the better solution. As you can see, pretty easy to implement. But interestingly enough, sometimes we want to explicitly actually not use the normals. And to show this, let me actually use something more complex like the toy. And we can just copy our point wrangle here. And here you can already see what's happening. Let's quickly change the scale, of course, by just adding a size parameter. There you go. And now we make it a bit finer and less strong, and maybe a normal afterwards to fix it. And here you can see, if we're not careful, you can see that stuff like this happens. And this is because basically every point moves in a different direction based on its normal. And that means they're not necessarily consistent. They use the same noise, but they interpret it differently based on their normals. Now, to explain why sometimes that is a problem, let's just compare it with another version. So I move this to the side and merge it together. And in this version on the right, let's actually get rid of the normal and add to the existing position without taking the normal into account. And the first thing you can already see is that, yes, okay, the deformation looks a bit weird. Let's actually add a little bit of a offset to that. driven by t. And here I think you can see the difference. When you deform each point by its normal, then you have, disconnected deformations. Whereas when you don't do that, can actually be the better idea, because then you can see things stay together because they share the same direction they move into. So this is a good thing to keep in mind. Technically, a deformation is based on the normal, but it's not always the right decision depending on what you want to do. And there's even one extreme case, and we will look at an example of this in the next video because it's really quite fascinating, is when you have a couple of points. Let's say we have a sphere that defines an area and we fill this with the points from volume, something like this. You can even go so far and say, you know what, I don't even need to add anything to the position. I completely replace it. For example, with a curl noise, and we add offset again, a simple one by just using the time. And what's interesting about this, when I put it into real time and also actually slow the whole thing down, maybe by this, you can see something really interesting happens. Because every single point is now completely overwritten by a curl noise, I basically have something like points in a simulation that are driven by a pop force, but without any simulation. This is purely Vex based. And when I've seen that, I've learned that from someone else. I think it was John Kunz actually. I was blown away because it's so simple, yet you have to realize that this is possible. Just drive the position of a point by a curl noise in a Vex code, and then you have something that looks a little bit like a swarm of, let's say, insects or something like that. Okay, so those are the three main ways that I would call how you can deform something. And it's not, again, it's not about one being better than the other or something like that, but it's really helpful to just keep in mind that those three ways exist. And one is to just add randomness or add a noise to the direction of the normal of the current position, and then add this to the current position. So roughly something like this. But sometimes it can also make sense, especially with more complex shapes, to really ignore this correct way of doing it and just adding a noise to something. And in my experience, this works best with a curl noise. And then this looks like this, that you have something that feels like it's driven from outside by something. So the shape is deformed in a consistent way. Maybe that's a good way of wording this, instead of deforming every point by itself. And the third way, which almost seems like the simplest way, is completely overwriting the position of something, which mostly makes sense in my experience with completely disconnected things like particles, where of course you could then later copy geometry to. And this is actually something we will do again in the next video. So yeah, I hope this was helpful. Thanks very much, and see you later. Cheers.